Let me share the slides just now. Okay, right. So basically, we're still in chapter 3, Introduction to Corrosion Electrochemistry. And what we have learned last week is probably on the types of the types of corrosion products. Okay, we have a few corrosion products of iron. We have learned like geotite, akaganite oxide, the hydrochloride, formation of the first rust product, which is known as hydroxide rust, and then followed by the other parts. Okay. I think we also have seen what would be the consideration in electrochemical corrosion process. We need understanding of anode and cathode. Anode is always a process of oxidation, while cathode is also the process of reduction. Okay, and yeah, probably today we are going to continue with the thermodynamic aspect on corrosion reaction. Okay. Right. Basically, nature is always concerned with minimizing the energy, and metals extracted from their ores are high in energy states, and they are not stable. As mentioned in the first 1 or 2 slides, I think last week, we have known that metals can be obtained from extractive metallurgy, from ore or metal scrap. And what happens is that when you have produced these pure metals, it is thermodynamically unstable, and it tends to return back to its more stable condition. In this case, why pure metal tends to react with the environment to form metal oxide or so-called rust. And the process itself is known as corrosion. The thermodynamic tendency for an electrochemical reaction to occur, such as metal corrosion, is determined by the free energy changes associated with that reaction. Take the following symbol reaction. For example, you have like A plus B, the reactant, okay, forming a product of C plus D. The free energy change associated with the above reaction can be expressed in terms of energy formation of each species with the reaction. So the overall free energy is basically the results of the products minus with the reactant. So you have actually a change of energy, okay, so-called delta G. And delta G is always related with equilibrium K, where K is actually equal to the concentrations of product over reactant. Okay, and things that you need to remember as well is that delta G, okay, delta G over here is actually a free energy not in the standard condition. That is actually equals to the free energy or delta G naught, okay, in the standard state minus with RT ln K. Okay, so this is actually the first reaction that you will have if it happens that you know in a corrosion process is always reacted with reactant to products. Okay, so when you have a reactant to product, for example, you have A plus B forming to C. Okay. Oops. C plus D, and the overall reaction is actually related with the changes of energy, because basically if you look at the energy diagram, this actually reactant and this actually products. Okay. The minimum energy needed to overcome actually known as activation energy, and the total energy, okay, for the formation of product, okay, is actually known as delta G. So that is why delta G at the end you will have is actually equals to the difference or the changes of energy from products, okay, to reactant G. Yeah, I put over here G. Okay, all right. So at the end, what you are going to get is that delta G is also equivalent to delta G naught, okay, minus with RT ln K. Okay, because basically K is actually means that the concentration or the activity of your products, okay, over the reactant. The tendency to metal to corrode is determined by the free energy difference between the metal and its corrosion product. And noted that delta G is the minimum amount of energy required to drive the molecules or the atoms over the activation energy barrier so that the appreciable reaction can take place. Of course, this is actually known to you guys that for a spontaneous process, delta G must be negative. So whenever you see the delta G is actually equal negative, then immediately you know that when you put the reactant, immediately it will form a product. Then this process is known to be spontaneous, right? Nernst equation, as you know, is basically the measurement of potential in a non-standard condition. The free energy can be related with Nernst equation using a Faraday's law. Because in Faraday's law, okay, in Faraday's law, the relation between free energy and potential is always delta G equals to negative NF over NFE, sorry, where E is actually the cell potential, okay? And this cell potential is actually obtained from the Nernst representation, where E cell is actually equals to E cell naught, the cell potential standard, minus with RT over NF ln product over reactant. So this is actually the same thing. If you actually substitute to this part, you will have another form of equation. Right. The standard condition that we always talk about is actually when the temperature is equals to 25 degrees C or equals to 298 Kelvin with R value or the gas constant value equals to 8.3143 joule over mole Kelvin. Okay, then when you substitute this value, then you get this simplified form. Earlier we have seen that it is actually in ln, change it into log, then what happened is you put a standard value 2.3 over here, then when you multiply it with this value, you will get 0.059. Okay, so consider the corrosion of zinc in HCl. So this actually the reaction that you will see. The formation of zinc chloride plus with hydrogen gas. Okay, so zinc chloride is assumed as the oxidized form of zinc, okay, because the half cell reaction at anode is basically the formation of zinc 2 plus. When zinc 2 plus actually reacted with Cl minus, then it will form zinc chloride. Meanwhile, the reduction process occurs at cathode is basically the formation of hydrogen gas, 2H plus plus 2 electrons, the two electrons actually produced from the anode will be transferred, okay, to the cathode and will be used for the formation of hydrogen gas, okay. And at the end, you can basically see the cell potential, or the overall potential is basically the potential of cathode, which in this case 0 minus with minus 0.763. This is basically the standard potential of zinc. Then you will get the value of cell potential equal to 0.7 positive. So that is why it means over here, the potential of the corrosion reaction must be positive. Okay, so when the cell potential positive, then it indicates that the process is basically spontaneous. Right. The consideration of non-standard condition can be seen as follows. Of course, this have been, I think, discussed earlier. Non-standard condition, if you have a temperature which is not equal to 25 degrees C, okay, pressure which is not equal to 1 atm, what else? I mean, like concentration is not equal to 1 molar, then all these are actually the consideration for non-standard. So you see over here that for non-standard state, the changes of energy will always become like this, okay, that you have seen just now. And the departure of free energy in a non-standard state from the standard state is as follows. You will actually deduct or subtract the non-standard values with the standard values. Okay? The corrected concentration of A available for the reaction is known as the activity of A and is given as this one. Okay. Right. So the next equation, okay, for this kind of non-standard condition can be substitutes. Okay, and you will get a simpler representation after you have probably do the math, and finally you can get a term like this. I mean, for non-standard condition, okay, of this equation. Another thing that I want you to remember is that for pH, if you want to relate pH, because pH is always related with the activity or the concentration of H plus, then over here you will see that there's a component of H plus, okay, log H plus over here, that it can be simplified to form this term, pH. Any questions so far? Anything that you want to ask? Okay. Okay, so we are moving on to the next part, which is known as Pourbaix diagram. So Pourbaix diagram is basically a type of diagram to indicate the region or the phase of a material, whether it experiences corrosion, immunity, or passivity. Okay, it functions like a phase diagram, but the relation between phase diagram is basically like temperature with composition, but for Pourbaix diagram is actually a correlation between potential with pH. Okay, so what is actually Pourbaix diagram is all about? As I said, Pourbaix diagram is actually a diagram used to detect the phase or the phases of a material. In this case, we are talking about metals, whether it will be immunity, corrosive, or passive. Okay, So for Pourbaix, the diagram is actually a relation of potential versus pH. Okay. The name itself is actually invented by a French scientist that actually used the Nernst equation to develop a relationship between potential and the solution pH, and to predict whether the metal will be immune, active, or passive. Active means corrosive, right? This diagram therefore maps the state of electrode as a function of both potential and pH. Diagrams were constructed based on the thermodynamic data and are available for pure metals. The kinetic data used by Pourbaix was the solubility products of the reaction, and assuming that metallic ionic concentration is around 10 to the power of minus 6 molar. Right. The Pourbaix diagram is commonly used by corrosion engineer to determine the pH and potential where a metal will either be stable to corrosion, will corrode, or will form a passive layer. So this is actually a very good indication, because when you do monitoring, for example, if you want to check the pipe, you have a pipeline in environment, and you want to know whether the pipe actually experience immunity, corrosion, or passive, then what you will do is you will make this as your working electrodes. You will connect it into a reference electrode, okay, RE, to check what will be the potential value, okay? And then you will also measure what will be the pH of your environment, okay? So at the end, what you will see is that you will try to match, okay, the value obtained with the diagram, so that you know. So meaning that for each and every materials or metal have its own Pourbaix diagram. It actually didn't mean that you can use this Pourbaix diagram for all types of metal. Each metal will have its own Pourbaix diagram. Okay, right. So this is basically the examples that given here. If you have like hydrogen as a consideration in your electrolyte, and if you have oxygen, then you know that the oxygen will produce hydroxide ions, or actually produce water. Then this is actually the examples of a Pourbaix diagram. So this is actually a Pourbaix diagram of iron. So you have here potential versus with pH, and over here, region number 1, okay, colored over here, is actually a corrosive region. So if you look to the examples that I showed to you just now, okay, when you do the measurement, the pipes, you detect what will be the potential value and what will be the pH value. Then you just check whether it will be in which region. Okay, so if the potential value is lower, then it means that it lies into the immunity region. So what does it mean by immunity? Immunity means that the corrosion process is impossible, meaning that this region, the metal will exist as a pure form. Okay, so this is actually the region that people always wanted. Okay, they want the metal to be always in the pure form without experiencing corrosion or passivity, right? So if actually it lies to this region, what happened? So if the potential value is slightly positive, remember, if you have potential that is positive, okay, it means that your delta G will become negative, and this indicates that the process will become spontaneous. And when you have a spontaneous process, this actually indicates that the corrosion can easily occur. Therefore, if you remember that anything that deals with a more negative potential values, okay, during the measurement, this will actually indicate that the delta G value will be will be positive, and the corrosion will be less likely to occur, right? And you have also a region over here, number 3, passive region, this region. So passive region, it means the insoluble protective layer of hydroxide or oxide layer is already formed, okay? So this region where you have the formation of Fe2+, okay? This is the region where you have Fe only, and this is actually the region where you have the formation of oxide, probably like Fe2O3, okay, or other types of rust product. It means that in the passive region, oxide layer have already formed. Okay, so when you have an oxide layer, okay, then it means that the surface is now become stable. Okay, that is why it means over here the most stable form. Okay, all right. So when you have a stable form, then this means that corrosion is already occur and already forming the oxide layer. Okay, any question so far for Pourbaix diagram? Is it clear to everyone? Madi, is it okay for you?
It's okay, Doctor.
Right. So this is actually the other explanation for Pourbaix diagram, because just now we have seen that when you have a more positive potential like this region, I just like colored it with red. Okay. So this region is known as active or corrosive. This region is known to be immune. And this region, let's color it with another color. Okay, it's known to be passive. This is actually the types of product that you would be expected. When you have a potential range between minus 0.4 to like positive 0.7 or 0.8, then you will have the formation of Fe2+. When you have a more positive, it means that it's already becoming more oxidation number. And here it's already like Fe3 plus. This one is Fe2+. Okay, and the rest is actually after it already forming the oxide layer. You have a Fe2O3. Okay, you have a ferric oxide. You can also have magnetite formation. You can also have ferrous hydroxide formation. Okay, over here. Actually, it's the same thing, just to explain about the formation of different types of rust at different pH and also potential, but probably just to relate with the Nernst equation. This is not something that you have to remember. I mean, just for your information only. I mean, you don't have to remember which region actually becomes Fe3+, Fe2+, or whatsoever. So just for you to know that, okay, when I do the measurement of iron, okay, then I will get this value. So I can actually indicate which region is it, whether it's active, immune, or even passive. Right. So the application and limitation of Pourbaix diagram. So since it is basically constructed from potential to pH diagram, we can actually formulate the corrosion control methods if you know what will be the condition. For example, I still remember my experience with an industry where we want to troubleshoot the problems. They are doing a processing of a hard disk drive. They do a washing using aluminium and a surfactant. So what happened is that the hard disk drive, aluminium hard disk, corroded. So they asked me what actually condition that is best for that particular material. So what happened is that actually we study the Pourbaix diagram, and then we measure what will be the pH and the potential value. So after that, we know that, okay, we have to adjust the pH so that the potential value will be more more negative, and with that we can actually control the corrosion. Right. So it also used for the identification of possible corroding states. If you want to know whether it forms a Fe2 plus, Fe3 plus, if you have the aluminium, you have also a different set of Pourbaix diagram. Okay. Can also give a prediction. Okay. The corrosion products and other types. But of course, Pourbaix diagram have its own limitation because the Pourbaix diagram is actually constructed at the standard condition, which means it is constructed at 25 degrees Celsius. If you change the temperature, then the Pourbaix diagram of that particular material will be different as well. So it cannot relate with thermodynamics data. If you have like different temperature, then you cannot assume what will be the condition. It's not the same as in the standard condition. It is for pure metal in the pure water system. If you're talking about alloys, okay, carbon steel, stainless steel, and whatnot, then you cannot actually refer to the Pourbaix diagram of a pure iron because it's totally different thing. You have alloys, then you have a different properties. Then it has its own Pourbaix diagram features. So no kinetic information is given. Kinetic is always related with time. You have a time duration, a time difference. So if you want to know at which time does this product occurs, it cannot relate with the kinetics. And the other things will be like other effects will be not taken into consideration if actually you want to know the effect of anions like chloride ions. It cannot tell you because everything is done at one specific condition. If you do it with water, then it's just water, not with the effect of chloride. Then if you want to study different chloride, then of course it will have a different Pourbaix diagram as well. Okay. Right. And finally, didn't take into account the mechanics, okay, the fluid mobility, okay, the flow and the velocity of solution. So always concerning with electrolyte in closed system and stagnant, not moving condition. Right. So any question about Pourbaix diagram before we move on to corrosion rate? Okay, so the other things that is interesting in corrosion is that we can actually evaluate the rate of reaction. Okay, so the corrosion rate is always an important measure to know whether the environment or whether the materials experience severe corrosion, moderate corrosion, or less corrosion. So that is actually different sets of formula used to calculate the corrosion rate. For example, this one, you see there's two formulas showing you here. For this kind of equation or formula, it is used when you use weight loss method. So what does it mean by weight loss? Okay, so weight loss is actually a method where you have your specimen, a metal, been put in a container at a fixed volume, okay, and you know what will be the initial weight, okay. So after the dipping, after a certain time, okay, you will remove out the solution and you'll see that the material will experience some degradation or loss. So you will have a weight final after that. So the weight loss is basically a difference of mass before and after. Okay. And then the other consideration is that you know what will be the area, because this is actually a specific area. Okay. And you already know the time, a fixed time, and probably other than that, the other parameters. So this is actually the methods known to be weight loss. Weight loss is also a method where the corrosion occurs naturally. You put the metals in the environment and it will corrode naturally. You didn't actually connect it with some supply to actually impress or accelerate the process. So that method is known as electrochemical assisted method. Meanwhile, for this one is more or less for natural occurring corrosion process. It is always expressed as the corrosion penetration rate, the thickness loss of materials per unit of time and area. So you have actually two formulas over here. 1, 2. Okay. The unit is actually in MPY. MPY is actually means mils of penetration per year. Mils is actually a unit of distance. This is actually a unit of, I think in the US, and they use miles or mils, okay, for distance. Okay, so it means that how much distance the penetration happens from the surface. So over here, the two formulas actually differ in terms of the unit. You have the first formula, R equals to 5.34 W over rho multiplied with A multiplied with T. W is actually the weight loss or the mass loss in milligram. Okay, milligram. Okay. 534 is actually a standard number. Okay. This one probably calculated after you have take into consideration all the other parameters. Rho is actually the density. The density of what? Density of metals. Okay. Density of metals. For iron, okay, the density is equals to 7.87 gram over centimeter cube. Right? Area for the formula first is actually in inch square, and time will be in hours. Meanwhile, for formula number 2, the formula is R equals to 87.6 multiplied with W. W is the weight loss. Unit still the same, milligram, over rho times area and T. So T is actually the time. Time is also in hours. Density is also in gram centimeter cube. Okay, area over here is actually in centimeters square, not in inches. So that actually makes the difference. And in fact, the unit is also different. This one is actually in mils per year, and the second formula is actually in MMPY. Yeah? MMPY stands for millimils per year. Okay, millimils per year. So far, if you use formula 1 and 2, you cannot actually relate current or other electrochemical terms into your calculation. So far, it's just always related with the waste loss, okay, and area, time, the duration of your dipping, and whatsoever. Okay. But for this one, we have another formula, okay, to calculate corrosion rate or even metal loss, which basically relating to the corrosion current, okay. So the formula that we'll use is actually known as Faraday's law. In Faraday's law, so you have lots of Faraday's law. Okay. Metal loss M is equals to IT MW over NF. Okay, because over here, Faradays have already told that the mass loss is always related with charge. Q is actually charge. And how you can make charge? Actually, charge is Q is equals to current multiplied with time. Charge of a molecular weight, in a molecular weight over the valency of the metals multiplied with Faraday constant. So if I expand, I will get this. This is a formula that I need to remember, or for you guys to remember, right? So what is I? I is actually current in amperes. Okay. T is actually time in second. MW is basically the molecular weight. Okay, the molecular weight of your metals. N is actually the valency, and then F is actually Faraday constant. Okay, so the molecular weight of iron, 55.85 gram over mole. For aluminium is always different. I think 20 something, 27 point something, copper something. Okay, and the valency for iron is equal to 2. Okay, Faraday's constant is equal to 96,500 coulombs. Okay, so all these are actually a few things that you need to remember. Okay. So this how you relate mass loss with current, but how you can calculate corrosion rate. So corrosion rate unit is actually in mmPy, can be calculated as M is actually here, over area times with time rho, or equals to I, small I, MW over rho NF. Okay, so both actually will give you the same value. If you want to calculate the corrosion rate based on mass loss or metal loss, you can use this one. Or if you have a current value, you can actually convert it into current density, okay? Because I is actually current, and small I is actually current density. So what is actually current density? Current density is basically current over area. Okay? All right. So that is why if you substitute over here, the M, this term over here, you will get this one. Yes. Eventually, it will be like current over area. So you will cancel it off. It will become current density. In fact, you can also have a molecular weight over N. So it is also known as equivalent weight. Equivalent weight is actually molecular weight over valency. Then I can also simplify this to become I ME W, equivalent weight, over rho F. So you can use either one. Which one do you want? It depends on your preference. Okay, But basically, this is the formula how you can calculate corrosion rate using Faraday's law to relate it with current. Okay. So generally, if you want to calculate the rate in moles over meter square over second, this is actually the formula that you will use. Okay. Current density over NF. Right. So there's also another formula to calculate corrosion rate. Okay. This one and this one. Maybe I will give this as number 3 to calculate corrosion rate. The first two is from the previous slides. And this one is actually 4 and 5. Okay. So 4 and 5 is actually used for if you do electrochemical measurement using potentiostat. Because over here, okay, equation number 1, 2, and 3, you calculate the corrosion rate based on weight loss method. The method that the corrosion occurs naturally, not an accelerated process. Okay. So for accelerated process, like using potentiostat, you will use this formula. Normally, we'll use this one, number 4. Okay, right. So the formula is actually R. The unit is an MPY, means per year, equals to 0.13 multiplied with I core, okay, small I, okay, current density, multiplied with equivalent weight. Equivalent weight, I've already told you, it is actually molecular weight over valency over rho, or the density of the metal. And things that you need to note over here is that the I core, the small I value must be in microamperes. If the value is not in microamperes, then you have to multiply with 10 power of 6. Then you will get in microamperes. This one is actually another formula. It's almost the same, except that the unit is different. This one is mils per year, and this is mils per year. Then the unit or the constant value over here is not the same. Okay. All right. So in case of you have alloys, because the alloys you will have a different composition of element, then you actually need to consider each percentage. For example, stainless steel, SS304, it has a composition of 90% of chromium, okay, with a valency of 3, nickel 9.25% with a valency of 2, iron, and the remaining iron 71% with a valency of 2. Then you need to find the equivalent fraction, the mass fraction values, which is actually equals to this. Okay, you have the percentage multiplied with valency over, okay, this is actually the atomic mass or the molecular mass of chromium. Okay, so this part is actually for chromium. You have a percentage multiplied with valency over the molecular weight of chromium. Okay, plus with this one is basically for nickel, and this one is actually for iron. So at the end, you will have a so-called like average, okay, average equivalent weight of your alloy. Okay, so this is actually important when you have alloy. If you have pure metals, then pure iron or whatnot, then you will use this formula straight away without calculating the equivalent weight. So once you use alloys, then you have to find the average equivalent weight. Then it will be substitutes over here, average equivalent weight. So for the mass loss using this one, you will substitute here. Okay. All right. all the while we are talking about mils per year, about the unit for corrosion rate, then there's also a conversion unit that you need to remember. Okay, so we have a different units for corrosion rate. We have milliamperes over centimeter square. We have mils per year, gram meter square over day. Okay, so I think the most commonly used is that the conversion from MPY to MMPY. Okay, to MMPY or MMPY to MPY. This is the common, I think, conversion that you need to see. For example, I want it to be reported as as MMPY. So the initial unit, okay. So this is actually the initial unit. Okay, MMPY, I want to convert to MPY, then I will multiply with a factor 0.0254. If I want to convert from MMPY to MPY, then I will multiply with this. Okay, this factor. I guess maybe if you want to remember all values, it's not important. Maybe you just remember these two values, then will be enough for your exam or your test. All right, so this is actually an example. If you have iron, okay, you want to convert the units. So 1 milliamperes is actually equals to 16 millimeters per year, equals to 456 mils per year, and also equals to 249 grams over meter square per day. Okay. So maybe we can take an example. I guess all the while we are talking about corrosion rate without seeing the examples. Okay. So in example 11.2, suppose that a corrosion cell composed of copper and zinc, okay, the current density at the copper cathode is 0.05 amperes over centimeter square. The area of both copper and zinc electrode is 100 centimeters square. First, calculate the corrosion current. Second, the current density at zinc anode. And thirdly, the zinc loss per hour. I guess this example is not included in your notes with a purpose. Okay, so you can jot it down for a while. But before that, just want to ask you, if you have this kind of setup, so imagine that you have over here copper plate and also zinc connected to a voltmeter. Okay, so dip in the solution. All right, so my first question is, what will be the anode and what will be the cathode? Anyone can answer that?
Zinc will be the anode.
Okay, zinc will be the anode. Mariam,
Mariam.
Okay, thank you, Mariam. Zinc will be anode and copper will be cathode. Correct? What's the reason? Because if you look the standard potential for zinc, this equal to 0.7, and this one is actually equals to probably positive 0.3. Okay, so you know that this will be anode and this will be cathode. Right. Then the at anode, you know that the reaction will be the formation of zinc 2+. Okay, so the electron produced, the current, okay, flow will be from anode to cathode. Then Oops. Then at cathode, it will be the reduction process. Cu2 plus 2 electron, the one that received from anode will form copper. Okay, so this is actually the basic things. But the question is actually asking what would be the current. Okay, given that the current density at cathode, copper cathode, current density of copper is equals to 0.05 amperes over centimeter square. The area, okay, of both copper and zinc, meaning that the dimension, the size of both electrodes are the same. Okay, the area is actually equals to 100 centimeter square. The first question is actually what will be the corrosion current? Okay, so if you recall back what I've told you, current density is actually equals to current over area. Then, if you want to calculate current, you just rearrange that, you will get current density multiplied with area. So what will be the current density? Here, the current density is equal to 0.05. Multiply with the area is equal to 100. Then you will get current is equals to 5 amperes. Okay, quite straightforward. I guess it's already shown in the solution. Number 2, the current density at zinc anode. Over here, the information given is just the current density of cathode, 0.05. Okay, so the total current that is actually used in the system is actually equals to 5 amperes. Okay. Then what will be the current density at zinc? Since, okay, the area is equals to 100, both are actually the same, and the total current value in the process, in the galvanic process, is equal to 5 amperes. Then you can calculate the current density of zinc, which is equals to current of the total process over the area of zinc. In this case, 5 divided with 100 centimeter square, then you will get 0.05 ampere over centimeter square. The value will be the same for cathode as well. Okay. Oops. Pen is not functioning. Oh.
Victor, the current density should be in micro?
No, this one, you will get it in amperes because the information is actually given in amperes.
Oh, okay.
Yeah. So, not sure why my magic pen is not functioning. Okay, try again. Okay, and finally you can have this one, the question is actually on the zinc loss. The zinc loss is actually the mass loss. Okay. So you can actually calculate the mass loss using the Faradays formula as mentioned earlier. Okay. So what will be the formula? If still remember, the formula is actually equals to M. Okay, M is equals to IT. I is actually current, T is actually the time, and M is actually the molecular weight of of a metal over an F. N is basically the valency and F is actually the Faraday's constant. Can you guys hear me? I think I have some problem with my system. Can you guys hear me?
Yes,
Mari?
we can hear you.
Oh yeah, okay. Right. Suddenly I can hear me. So as I said, M is actually equals to uh, the problem with my pen. No. So here current we obtain it equals to time.
Sir, we can't hear you clearly.
Sorry, what?
We
Again,
can't
Madi?
hear you clearly. We can't hear you clearly.
Now you can hear me?
Yeah, now yes.
Okay.
Okay.
Doctor, you make
Right.
any
So
addition
time is
slide?
basically
Doctor,
yes.
you make any addition in slide after both in the first time?
We might make what?
Any addition? Addition?
Yes, yes. As what I told you, this example is not included in the notes.
Yeah.
Yeah, so you can jot down.
Okay, okay.
Okay. Right. So time is basically mentioned 1 hour. So if you do the conversion, the time or the unit conversion, 1 hour is equals to how many minutes? 1 hour is equals to 60 minutes. And then 1 minute is equals to 60 seconds. And that's why I think you will get, let me actually insert some text box over here. It's suddenly my pen is not working. Okay, 1 hour it's equals to 60 minutes, and 1 minute it's equals to 60 seconds. Therefore, for 1 hour, you know that equals to 60 times 60, which eventually equals to 3,600. Okay, so that actually justifies why you get this. Because as I said, if you want to use this Faraday's formula, the time will be in second. Right? So 65.38 is basically the
Hello, doctor. Are you there? I can't hear you. Doctor, we didn't hear anything.
Okay. Now, can you guys hear me?
Yes, we can, but not clearly, Doctor.
Okay. All right. Very sorry. Suddenly we have this I think connection problem. It's just suddenly disconnected. Let me share the slides again. Okay, so can you guys see the slides now?
Yes, Doctor, we can.
Okay, all right. So very sorry about what happened just now. I guess just now we are talking about this one, the example, the previous example. Okay,
Okay, Doctor.
just now I told you that for this one, the time will be in seconds. So you have to 1 hour into second, converted 1 hour, and it becomes like 3,600 seconds. 65.38 is basically the atomic mass of zinc. Okay, And valency of zinc is actually equals to 2, and the Faraday constant is actually equals to 96,500. So when you substitute all values together, you will get the mass loss is actually equals to 6.1 grams. Okay? Right. Moving on to the next examples. You have an iron container of 10 cm times 10 cm at its base is filled with the heights of 20 centimeters with a corrosive liquid. A current is produced as a result of an electrolytic cell, and after 4 weeks, the container has decreased by weight in 70 grams. So first calculate the current, and number 2, the current density involved in the corrosion of iron. Okay. So to answer this question, actually you need to imagine how does the container look like. Okay. Perhaps maybe I can draw it a bit. Okay. Oh, I do have a problem with my pen actually. I don't know what happened. It suddenly becomes like that. Uh,
Today, doctor, many problems should occur.
Sorry again.
I say today many problems should occur.
Yeah, maybe because of it's the first day of Ramadan, so the system also are fasting. No
Every
energy.
people very angry.
Sorry, what?
Every people very angry.
Oh, every people are angry. Yeah. Oh, yes. Never mind. I draw it, not using my pen. Maybe just use this mouse. But it's hard actually. I'm used to draw using. Okay, so once again, very sorry. I'm not sure why today having so much problem. I mean, with the system and also the connection. Not sure why. Maybe the coverage not really good. So can you guys hear me? I mean, I hope yes. Madi.
Yes, Doctor.
Oh yeah, thank you very
Yes,
much,
Doctor,
Madi.
we can hear you.
I will quickly share the slides with you now, and see what we should continue. Okay, right. So here we go again. Where is it? Okay, I guess maybe we just like started with this one. Okay, so we have an iron container that is actually have a base of 10 times 10. So if you imagine that you have a container with a base of 10 times 10, okay, luckily this time my pen works well. Okay. Over here. All right. So you have a base of 10 times 10, and then it is filled to the heights of 20 centimeters with a corrosive liquid, probably like acid or whatsoever. Okay, a current is produced as a result of electrolytic cell after 4 weeks, and the container has by 70 grams. Okay, calculate the current and then current density involved in the corrosion process. So the first question is basically asking about the current. Okay, so you can actually understand that the formula that relates mass loss with current is mass equals to IT MW over NF. This is basically your formula, okay, to calculate mass loss. You can actually rearrange it. I, okay, is equals to mass multiplied with NF over T with MW. Okay. So this is actually the formula that we are going to use, because basically the first question is actually asking about current, right? So time given over here is basically for 4 weeks. Okay, so let's do the unit conversion. You have a 4 weeks. Okay, so 1 week equals to how many days? Jihad, 1 week equals to how many days?
7, Doctor. 4
1
weeks,
day
28.
equal to how many hours?
24.
24 hours. 1 hour is equals to how many minutes?
60.
60. And 1 minute equal to
60 seconds.
60 seconds. All right. So you can actually do the conversion. Okay. The exposure is actually for 4 weeks. So 4 times with 7 times with 24 times with 60 times with 60. This will give you 2.42 times 10 power of 6 seconds. Okay? All right. So what will be the other information? The other information is already given. Mass loss is equal to 70 grams. And because this is actually for iron, is equal to 2. Faraday's constant is equal to 96,500 coulombs. Molecular weight 55.85 grams over mole. Okay, and you can actually substitute those values. Put it here, 70 times with 2 times with 96,500 divided by the time in second, 2.42 times 10 power of 6 times with the molecular mass, 55.85. Okay, then you will get the value, the current is actually equal to 0.1 amperes. Second question asking about the current density. So current density is equals to current over area. Okay, so current over area, you have the current value 0.1, and now what will be the area? Okay, so the area is actually the exposed area for the corrosion. You see this is actually a container. So where does the corrosion occurs? It will be on the base and also on the sides. So how many base and how many sides that you have? Answer is given there. Liana, what do you think?
So we have one base and 4 sides.
Yeah, 4 sides because it's like actually in a container, like we assume it's like a cube or cuboid, right? Okay, you have like 4 sides and then we have like one base. But another thing that I want to ask, do we count the top, not the base, the top or the lid of the container?
I don't think so.
Why?
As long as it does not dia tak terkena dengan that corrosion punya side.
All right. So basically, the container we have to assume that it is an open lid container. Open lid container means that it is not closed. So if it is a closed container, then of course we will consider that. So that is why I think only one base plus with 4 sides that you need to consider for your area. One base, so base 10 times 10 plus with 4 sides. So you have 4 multiplied with 20 times with 10. This is actually the area of the sides. So at the end, the total area will be equals to 900 centimeter square. Then over here, you can calculate the current density equals to 0.1 divided with the area, 900. Then this will give you the answer 1.11 times 10 power of minus 4 amperes over centimeter square. Okay? All right. So, additional question. What will be the corrosion rate? Anyone wanted to try? What will be the corrosion rate? So what would be the formula for corrosion rate if you still remember? So corrosion rate, CR, okay, unit is actually in what? MMPY or MPY?
One micro, one in inch, 1 in centimeter.
You can actually refer to this one back, okay? The unit is actually in MMPY. This is actually the formula. You have corrosion rate equals to M over area times time times rho, or you can use this one. Okay, so we're back to here. Oops. Okay, or you can also use this formula. Okay, all right. So if you substitute the value, if you didn't want to use current density, you just like directly calculate it as 70 over area is equal to 900. Multiply with the density of iron. Density of iron 7.87. Multiply with the total time. Total time just now is what? Equals to 2.42 times 10 power of 6. Okay. So can you just press a calculator and see what's the answer that you get for the corrosion rate? Can someone try? Diana, boleh tolong try ke?
Okay, jawapan dia 4.08 times
4.08.
times 10 to the power negative 9. Is it?
After I got 220360.
220. Do you use the same formula, Mahdi?
Yeah.
Anyone got a different answer? Let me check value. So just now, I think I told you that to calculate using either, formula, because both formula will give you the same corrosion rate. So just now you have the mass loss equal to 70, okay, and then area is equal to 900, okay. So 900
I get
multiplied with
0.0098.
0.0098. I think just now, Liana, you got 4 point something, right?
Yes, Doctor.
Okay, never mind. How about others? Anyone got the same answer with either Liana or Mahdi?
I got the same answer with Yana.
Okay. And Nazira ada try ke?
Sama dengan Liana.
Okay, so 900, we just try again. 900 multiplied with the density, 7.87, multiplied with the area. Area is equals to 2.4 times 10 power of 6. Nine times 10 power of
How much area?
Sorry?
How much area?
Area, the same area that we are using, 900.
I think 3.5.
I got 4.14 times 10 power of minus 10.
Doctor,
Betul
70.
Diana?
Minus
70.
negative 9.
Minus 9.
Minus
Minus 9. Yes, I got 4.142 times 10 power of minus 9. Yeah, the same thing?
Doctor, 70 multiplied by 1.11 multiplied by 10 to the power minus 4 over 900. over 2.42 multiplied by 10 square 6, yeah?
You use this formula or this one, Jihad?
The second.
The second one.
Mm.
Actually, if you use the second one, you also get the same thing. You should get the same thing. I mean, you get the same thing?
I do not know.
So if you use the second formula, the current density 1.1 times 10 power of 1.1 times 10 power of minus 4, okay, multiply with
70.
55.85, okay, divided with the density 7.87 times 2 times 96,500.
Okay.
Got the same value?
Okay.
MMPY, don't forget the unit. Okay, so this additional question, if let's say I would like to answer, I mean, of course, this example, I want you guys to digest it, because normally for this chapter, if I want to ask in exam or test about corrosion rate, I will give almost the same situation as this, okay? Meaning that you know how to convert time into second, you know how to calculate area, you know how to calculate current or current density using the Faradays equation. Okay, so maybe before we call for the day for today's lecture, I just want to give another examples. Maybe if you can snap the photo or you can actually jot down this question, we can do it together. Okay, this is actually another set of question that this is from past year question. I mean, like I give this question to students before, both undergraduate and also postgraduate. I mean, undergraduate in materials chemistry. All right, so you have like a pipe. A carbon steel pipeline is used to transport sour crude oil that contains 3.14%, which is equal to 31,400 ppm of corrosive hydrogen sulfide, H2S. After 3 months, it is removed for maintenance check. It is observed that the carbon steel pipeline produced a weight loss of 5.2 grams. Using Faraday law, calculate first one, current density, second one, the corrosion rate of carbon steel pipeline in MMPY. So I give you all the information. Okay, the molar mass of iron is equal to 55.85, valency 2, Faraday constant 96,500, density 7.85 grams centimeter cube, and circumference. This is actually the keywords. Circumference formula is equals to 2 pi r. Okay. Do you guys want to try it? Okay. So probably we just jot down what will be the information given in this question. Mass loss. What will be the mass loss? 5.2 grams. Okay. Valency equal to 2. Faraday's constant is equals to 96,500. Okay. Equivalent weight or molecular weight, sorry, is equal to 55.85 gram per mole. And then what else? Density is equal to 7.85 or 87 gram over centimeter cube. Okay. Time is equals to 3 months. Okay. So what formula that we are going to use? Of course, when it talks about current density, you know that you have to find current first. So mass loss is equal to current multiplied with time multiplied with molecular weight over what?
NF.
NF. Very good, Madi. Okay. And then another formula Okay, sorry. Current density is equals to what? Shamira, current density is equal to what?
Current over area.
Current over area. Very good. Okay. So we are going to use these two formula to answer question number 1. Normally this set of question, even the previous slide, this question alone can carry as much as 10 to 15 marks. Normally like this one, I give like 15 marks. So in exam, normally one question will carry around 20 marks. So this is actually more than half of the marks is actually coming from this question alone. So that is why I want you to really understand how to calculate what will be the formula will be used, okay, to answer this kind of question. Okay, all right. So now we try to rearrange this formula. It is now becoming current equals to mass multiplied with NF over time multiplied with MW. And later on, the strategy is after you get current, you will calculate current density using this formula. Okay? Then you need to find the area and whatnot. Okay. So first, I think maybe I will just like give some tasks for each of you to calculate. Okay. So for time conversion, maybe I can ask Nazira to help for time. Can you actually convert it into second? Others can actually try and maybe we can cross-check the values after this. Nazira, boleh ke?
Boleh.
Okay. I just want to highlight to you that months. Okay. If you want to convert months, so 1 month equal to how many days? Nazira, satu bulan berapa hari? 1 month equal to how many days?
30 or 31.
30 or 31. But which one you choose? If you want to use days, I will recommend you to use 30 days. Don't use 31, don't use 28, don't use 29. Use this 30 days. This is actually the average number of days per year. Okay? And then after this, you can easily convert into hours and whatsoever. 1 day equals to 24 hours. Oops. 24 hours. Okay? 1 hour equals to 3,600 seconds. If you want to convert into weeks also you can. Like 1 month, how many weeks? 1 month equals to 4 weeks. We have like around 4 weeks. Then 1 week you have like around 7 days and the rest. But the problem is if you use weeks, then you are not going to have the same days. It will be like around 28 days. So the answer will be slightly different. But I guess that is normally, I mean, I wouldn't recommend you to use weeks. I will rather ask you to use in days. Okay? Use 30 days to be safe. Okay? So can you try, Nazira? What is the answer that you get? Three times with 30, times with 24, times with 3,600. Answer? How many seconds?
2.59 to the power of 6.
Sorry again?
Uh, 7.78 to the power of 6.
Did everyone got the same answer?
Yes, doctor.
Okay. All right. So we can actually calculate the first one. But before that, maybe we can find what will be the area. This will be easier for us to calculate the current density next. Area. So how actually we are going to calculate the area? Because this is actually like a hollow tube. You have to imagine that the gas is being like transferred across the pipe. So you have an open end of a pipe. Then if I ask you, if this pipe is being used to transport like sour gas, which part actually you think will be corroded most? The most corroded one.
The inner
The
wall?
internal part.
The internal part, yes. Of course, the internal part will be corroded. So meaning that what you should get is actually you should know what will be the area of the internal cylinder, the internal part. So how you are going to calculate that? Anyone knows? I think I give you the clue over here, circumference. Anything to deal with circumference? Hamda?
Yes, sir. It
Actually, circumference is to calculate the circumference of your cylinder. Okay. So as you noted earlier that when we transport the sour gas or the corrosive environment to this pipe, this internal part will be corroded. Okay. Imagine that if I cut this pipe, just cut like one part of it, just one part, not two parts. Then if I like open it, it will be like a piece of paper like this. Okay, it will be like open as this. Okay, so the circumference actually will be like this is actually the circumference, and this is actually the length. The length over here is mentioned that is equal to 20 meters. Okay, 1 meter is equal to how many centimeter?
2000.
Centimeters.
100.
100.
Yes, 100 centimeters. Okay, so you know that this one you have to 20 times with 100. You get what? 2000. Okay, 2000 centimeters. Because we have to convert to centimeters. Remember, area will be in centimeters. Okay, so what will be the circumference? So the circumference actually need to be calculated because over here, I think I give you the radius, the diameter. Diameter of the pipe is equals to 20 overall, and the thickness is equal to 2. Internal diameter. Internal diameter is equal to what?
16.
16. 16 or 18?
16.
16. Yeah, 16 lah. Because you have 2 centimeters over here. You also have 2 centimeters over here. Not 18. Okay. 2 cm. So 20 minus with 4, you get 60. 16. Diameter, ID, I just put internal diameter is equals to 20 minus with 2 minus with 2, you get 16 centimeters. Okay. All right. So circumference is equals to 2 pi r. Okay. So 2 multiply with pi multiply with r. What is r? R will be 60. Oh no, not 16. 16 divided with 2. Because this actually diameter. R is actually radius. Then can someone calculate this one? Maybe I think like you get like around 8. 8 times with 2. Get like 16 again. 16 pi. So 16 multiplied with pi. What value you get?
50.26.
50.26 cm, eh? Okay. Right. So this now will become 50.26 centimeters. So the area will be the circumference, which is 55.26 multiplied with 2000 centimeters. What is the value? .26 multiplied with 2000.
1.01
1.01
times 10 to the power of 5.
power of 4.
5. 5.
5.
Uh-huh.
Same square. Eh? So this is actually your area. Okay, so we have everything. We have time, we have area, we have everything now. So we just need to put it here. 5.2 multiply with 2 multiply with Faraday constant. Hamda, can you calculate this? I think the rest also you can calculate, and we can check the answer later. 5.2 multiply with 2, this is the valency, multiply with Faraday constant, multiply over the time, 7.78 times 10 power 6, multiply with 55.85. Answer? Atira, are you following, Atira?
Yes, doctor. I'm calculating right now.
Oh, okay. Saya ingat Atira tadi dah keluar dah because of the disconnection.
Ada lagi.
Okay, very good. Okay, so what will be the answer?
For the
Hamda?
current,
Is Doctor calculating?
Calculating. Oh,
Doctor,
Atira, did you get it? Sorry, again?
2.3. 2.3
2.3.
I also got
multiplied by
2.3.
10 power
10 power of
8, I think.
2.3 power of
Multiply,
8.
minus 13. Choose minus 13.
Minus 13.
Yeah. Is that correct, Nadira, Hamda?
I got 2.31 into 10 to the power 13, not minus. I'm not sure.
No, that go from down. The
Atira,
power.
dapat jawapan sama ke Atira? Atira, did you get the same answer?
For the current, I get 2.3 times 10 to the power of negative 3.
Yeah.
Negative 3.
No, not negative.
Yeah, negative 3.
Not negative 13, eh? Jihad, you got minus 13.
Yeah, negative 13, yeah.
Mahdi?
Doctor, I got the same with
I didn't
Atira.
calculate.
Mahdi got, Shamira, Shamira got the same with Atira.
The power of negative 3.
Power of negative 3.
Yep.
Okay. Mahdi?
Yeah, Doctor.
Power of what you got? The same? Power of negative 13 or 3?
I didn't calculate. I'm calculating now.
Okay, let me calculate. Oh yeah, we just.
Okay.
5.2. Okay. 7.78.
Doctor, I recalculate and take the same answer.
Sorry again. Times 55.85. Four.
Victor, 2.3 multiplying 10 power minus 3.
How?
Yeah, I got it. Power of minus 3.
Yeah, minus 3.
Yeah,
But
I got it as well. Power of minus 2.3097. Power of negative 3. So it is not power of 13. So maybe
Okay.
Jihad, you...
I will recalculation another time.
Okay, no worries. Okay, so if you notice, this one is actually power of negative 3, or we can also write it as milliamperes, because this is actually power of 3, so you can actually write it as 2.3 milliamperes, or as this also no problem, 2.3 times 10 power of negative 3 amperes. So the next one is to calculate current density. So current density, you just substitute 2.3 times 10 power of negative 3 divided by 1.01 times 10 power of 5. Mariam, can you calculate this? What would be the answer?
2.277 times 10 to the power of negative 8.
2.27, times 10 power of
Negative 8.
negative 10.
8.
8.
8.
Mm.
Okay.
Yes.
Everyone got the same answer?
Yeah, I got the
Yes.
same answer, Doctor.
Okay, very good. So how about the last one? Corrosion rate of the carbon steel in mmPy. You can use this formula, either one of it. Maybe I just need the final answer. Corrosion rate. Liana, I think I asked Liana to calculate.
Okay, jap. Tengah calculate.
Okay, tak apa. Take your time. Got it?
Okay, 8.43.
8.43, yeah?
Times 10 to the power of negative 13.
Negative 13.
13. mm per
Okay.
y.
Everyone got the same answer? Shamira, dapat jawapan sama?
Sama, Doktor.
Jihad, did you get the same answer? Or you did calculate?
Yeah, that's correct.
Okay. All right. So if everyone got it right, then this will be the final answer. I will show you actually the marks distribution. If it happens that you are given this kind of question. Normally the unit conversion like this one, you will get like 2 marks each. 2 marks for time conversion, 2 marks for area conversion, 2 marks for circumference conversion. Okay. And then what else? For this one, normally if you write the formula, so that is why I want you to remember the formula. If you just write the formula, but the value, substitution value is wrong, you will get at least 1 mark over here. Okay. And when you insert the formula, I mean the values over here with this answer, maybe this one will carry like 2, this one final answer 1. Okay, all together, okay, this one alone 4 marks, and this one 2. Okay, current density. And this one, I think the corrosion rate also like around 2 marks. So if you count like all together, 2, 4, 6, 8, 8, and then you have 10 plus with 4, around 14 marks already for this part. So this is actually the distribution. I think now if it happens that you have been asked with this kind of question, you know that which part that contributes mark, then you know, okay, I should actually know how to calculate or to convert time, to convert area, to put the formula, because if you put the formula, at least you will get 1 mark. I try to help the students. Okay, all right. So before we end our lecture, I'm sorry to take your time today. Is there anything that you want to ask? Anything?
That's okay, Doctor.
Regarding the example here and here. Okay. So if there's no question, then be prepared for your third quiz on Thursday, because the third quiz will also ask about corrosion rate. So at least you know how to calculate this thing, and it will be asked during your quiz, on Thursday. So once again, thank you very much for your time. Thank you very much for your patience. I'm very sorry what happened just now, and hope to see you on Thursday. Thank you very much, and have a good day on the first day of Ramadan. Assalamualaikum warahmatullahi wabarakatuh.
Bye, Doctor. Ramadan Kareem.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you, Doctor. Happy
You're welcome.
fasting.
Thank you, Doctor.
You're welcome.
Thank you, Doctor. Happy Ramadan.